Math 2414, Taylor and Maclaurin series, video 11, addition and subtraction of series. The last 2 or 3 videos in this series of videos will just briefly show examples of how to combine 2 pre-existing series into a new series. Addition and subtraction is fairly straightforward. It's basically just combining like terms. So for example, let's find a series for the function f of x equals 2 times e to the x plus 3 times e to the negative x. If we look at this as the sum of 2 terms whose series we already know, but have coefficients, we know the series for e to the x, and we can easily adjust it so that it's the series for e to the negative x. So let's start by representing those series. E to the x is a series that you just flat out need to know. It's the sum n equals 0 to infinity, 1 over n factorial times x to the n. Now, if we want to adjust this to make a series for e to the negative x, all we have to do is replace the x with negative x in the sum. So we have the sum from n equals 1 to infinity of 1 over n factorial, negative x to the n. Then we can either pick up the coefficients or deal with the negative. I choose to deal with the negative. Because we can rewrite negative x to the n as negative 1 times x to the n, there is a distributive property of exponents over multiplication that allows us to separate the alternator and, more importantly, expose the x to the n that we have over here so we can more easily combine like terms. If we make that split, then we have that e to the negative x is the sum from n equals 0 to infinity of negative 1 to the nth power over n factorial times x to the n. Next, we'll pick up the coefficients, which will be really easy. We simply have to write the coefficient in front. And technically, you would write it outside the sum, but you can distribute it into the sum. And so 2e to the negative x will be the sum from n equals 0 to infinity of 2 over n factorial x to the n. And the same thing for 3e to the negative x. All we have to do is multiply the 3 across the sum, distributed into the sum, and it will just show up on top of the fraction along with the alternator. So 3 times negative 1 to the n power over n factorial times x to the n. And now that we have the series for 2e to the x and 3e to the negative x, in other words, we've got this series and this series, all we have to do is literally add them together. And so we get 2e to the x plus 3e to the negative x is equal to the sum. Now, it's important that your sums have some things in common before you just randomly put them together. Specifically, they should have the same lower limit and upper limit. Since these are infinite series, of course, they'll have the same upper limit. If they don't have the same lower limit, you can do a change of variable to fix that. Just remember that the name of the variable is actually immaterial. If we have a sum that starts with k equals 1, we can just change all the k's to n's or any other letter not currently being used. But it's important that your limits match, and to the best of your ability that you can make the powers of x match. That will be really important, as you're about to see. Okay, so if we add these together, we get the sum n equals 0 to infinity of 2 over n factorial x to the n plus 3 times negative 1 to the nth power over n factorial x to the n. Got a little premature with the parentheses there. But ideally, we would like this to be in proper power series form, the sum of a coefficient times the power of x, not with, excuse me, not with a giant plus sign in the middle. But that's easy to fix because if you notice, both halves of the addition problem have some common factors. Specifically, They both have n factorials in denominators. And they both have, of course, x to the n power. So if we factor that out, then we can write our best answer as the sum n equals 0 to infinity of 2 plus 3 times negative 1 to the n power all over n factorial times x to the n. And that would be a perfectly good answer. Put a box around that. So really adding and subtracting power series is fairly straightforward. The time where it becomes an issue is when you don't have matching exponents and things like that. For example, let's say we wanted to take a look at the power series for, let's keep it simple, sine of x plus cosine of x. And we wanted that power series. Well, we have the power series for each of these separately. I'm trying to erase that and draw a better x. Apparently it doesn't want me to do that. We know the power series for each of these separately, or at least we should. We know that sine of x is the sum n equals 0 to infinity. I know this is over the odd powers. So 2n plus 1 factorial x to the 2n plus 1. It's got an alternator that has to start out positive, so to the n. And we know cosine of x is equal to the sum of n equals 0 to infinity, negative 1 to the n, over 2n factorial x to the 2n. But the problem with just adding these together is we can't get the exponents to really match because they're currently different. If both of them just had x to the 2n power, that would be fine. And you might be brainstorming and say, well, can't we rewrite this as x times x to the 2n power? And you're right. And although that would make these powers match, we would still have that straight x. So sometimes when you're adding two series, you don't have the luxury of being able to force everything to play nicely so that we can just write one clean answer like we have in the red box down there. So what would we do with something like this? Well, let's start by actually writing out each series. We know that sine of x is equal to x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial. And then cosine of x is equal to 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial plus. So if you were to literally add these series together without using sigma notation, it would be 1 plus x minus x cubed, excuse me, getting ahead of myself, 1 plus x minus x squared over 2 factorial minus x cubed over 3 factorial plus x to the 4th over 4 factorial plus x to the 5th over 5 factorial minus x to the 6th over 6 factorial minus x to the 7th over 7 factorial, and then the next one would be a plus. And it's easy to point out patterns. This is kind of like the power series for e to the x, except it's got an alternator with a period of 2, meaning that it takes 2 terms for the signs to change each time. 2 positives, 2 negatives, 2 positives, 2 negatives. Is there a concise way to write this as a single sum? Well, the answer is yes, if you can come up with an expression for an alternator of period 2. Now, I know a sneaky way to make one happen. It involves something called the greatest integer function. But for now, let's just say that the best way to represent this sum is exactly how we see it. I've got other tricks up my sleeve, but I don't think I'm going to mess with them. All righty. Oh, that's something I really want to do. I think I'll do a supplemental video and make it an extra one because it's not really pushing the boundaries, actually not at all, but I wanted to point how to add and subtract series here. And to be honest, we didn't subtract any, but that's just a matter of keeping up with your signs.